A serious physics model says the Big Bang was a bounce. That means a prior universe contracted, then rebounded into ours. Heat rose, distances shrank, then space itself sprang outward like steel. Here, Big Bang means hot beginning, not ultimate birth of everything. Immediate takeaway: before can mean a physical phase with real dynamics. Gravity squeezes, while quantum effects push back at extreme densities. Several proposals compute that push using tested pieces of physics. One predicts a maximum density near the Planck scale. Planck density sits around 10 to the 96 kilograms per cubic meter. So before is not nothingness, but another lawful stage of spacetime. We can actually calculate scenarios where a prior phase seeds ours. Bottom line, physics lets before mean a genuine, earlier state. Step outside at night and you bathe in ancient microwaves. That glow is the cosmic microwave background, the sky's oldest light. It defines what Big Bang really means, a hot early universe. As plasma cooled, electrons grabbed protons and light finally traveled free. Space kept expanding, so those photons stretched into microwaves we detect. Tiny temperature ripples reveal tiny density variations from the first moments. We measure about 2.725 Kelvin, almost perfectly uniform across the sky. Fluctuations are near 1 part in 100,000. Its spectrum matches a perfect blackbody, better than 50,000 to 1. This matters because any earlier phase must reproduce those precise patterns. Change the timing and the peak positions slide the wrong way. Change the statistics and galaxies would clump in odd fashions. One sentence recap. Hot, dense, expanding is fixed by this fossil light, so any before must feed into that map without wrecking it. Stand on a rubber grid and watch every square collapse inward. A singularity is where curvature blows up in general relativity. That is a signal of missing physics, not a magical hatch. Einstein's equations steer freefall paths called geodesics through spacetime. Under strong gravity, those paths converge like cars funneling into tunnels. Energy conditions make the focusing unavoidable during collapse or rapid expansion. Hawking and Penrose proved many geodesics simply end within finite time. That end signals a breakdown where classical predictions cannot continue. Consider a black hole of 3 solar masses with 9-kilometer horizon. Cross it and tides spike beyond limit before your wristwatch ticks twice. Common mistake is treating infinity like reality, not a red flag. Bottom line, singularities are signposts that shout, bring quantum gravity here. Zoom closer until spacetime looks pixelated, like woven threads under strain. Loop quantum cosmology quantizes geometry into discrete chunks of volume. It matters because discreteness can tame infinities, avoiding dead ends. Spin networks carry quanta of area, assembling space from tiny tiles. Effective equations add a quantum pressure that grows near Planck density. As contraction intensifies, that pressure resists further crush, like a spring. When density reaches about 0.41 Planck, the motion flips into expansion. Perturbations thread across the bounce, altering their power at small scales. Some versions predict a cutoff or oscillations in the primordial spectrum. Example in real terms, contraction ends near 10 to the 96 density. Net result, discreteness acts like a spring, turning crunch into bounce. Watch space balloon so fast, distant points outrun any light. Inflation is accelerated expansion, driven by energy stored in a field. It matters because it explains smoothness, flatness, and early seeds. A scalar field rolls slowly down its potential, powering near exponential growth. Quantum jitters nudge that field differently in different regions of space. Some patches finish rolling, dump energy as heat, and form particles. Typical reheating temperatures can approach about 10 to the 27 Kelvin. Those jitters become density ripples, with a spectral tilt near 0.965. Gravitational waves may appear too, measured by the tensor to scalar ratio. Tiny test, find primordial B modes, and we read inflation's fingerprint. Bottom line, inflation sets the stage and maybe keeps spawning new regions. Walk to a globe's south pole and notice how directions blur. The no-boundary idea rounds off time, removing a starting edge. It matters because beginnings without edges can still be predictive. Path integrals sum over compact geometries that resemble tiny closed worlds. At minuscule scales, the dominant shapes look like curved de Sitter domes. Then a rotation in time turns those shapes into expanding spacetimes. The wave function weights different curvatures and different fluctuation amplitudes. Predictions lean toward near flatness, with perturbations near 10 to the minus 5. Some formulations prefer low initial entropy among the allowed possibilities. Rule of thumb, swap hard edges for probabilities, then follow the math. Net result, a before exists as a smooth cap, not a wall. Here fading ripples, then a fresh wave builds from the center. Cyclic cosmologies propose repeating phases across enormous cosmic timescales. They matter because repetition could reset conditions, avoiding singular starts. Ekpyrotic scenarios use very slow contraction to smooth and flatten space. High-pressure dynamics with equation of state W greater than 1 dominate. A brane collision or bounce then ignites a hot expansion phase. Conformal cyclic cosmology rescales infinity, stitching neighboring eons together. Black holes evaporate away, erasing scales and linking eon endpoints. Some groups claimed circular features in the microwave sky as evidence. Those claims remain debated because statistics are painfully tricky there. Common mistake is lumping cycles together when their predictions can conflict. Bottom line, cycles add rhythm but must meet sharp observational tests. Data streams across the sky while instruments scan with patient precision. A strong model matches existing measurements and risks fresh predictions. Otherwise, it drifts into metaphysics and loses scientific traction. Compare predicted spectra with surveys, including non-Gaussian fingerprints. Check curvature and isotropy using deep catalogs and weak lensing maps. Hunt relic gravitational waves through B-mode polarization in the microwave sky. Planck measured the spectral index near 0.965. It constrained local F sub NL near 0 within a few. Current surveys keep R below about 0.035. Future arrays aim to reach R near 1 times 10 to minus 3. One sentence recap, predictions must corner themselves, allowing clean refutation. So workable ideas survive only by matching and then predicting data. A cold, sparse cosmos stretches, while faint galaxies drift apart. The arrow of time points from lower to higher entropy. It matters because any before must explain that initial order. Gravity clumps matter, yet our earliest state was unusually smooth. If random fluctuations set starts, late branes dominate bizarrely, the Boltzmann problem. A bounce or cycle can reset conditions and curb that pathology. Entropy in the early plasma was huge, but geometrically special. By count, available microstates were smaller by about 10 to the 88. Today's supermassive black holes carry entropy near 10 to the 103. Low initial Weyl curvature is one proposed geometric selection rule. Tiny test, does your scenario select low entropy without fine-tuning? Bottom line, time's arrow rests on special starts that physics chooses. We began with a bounce and ended with sharpened possibilities. The hook was simple, a prior phase might have birthed ours. Now you know how real equations let that idea breathe. If this stretched your brain, share it with one friend. Thanks for exploring this strange, beautiful frontier with me.